All right, ladies and gentlemen, so it's the second day of Thermo, and we're going to get right into it with the math today. This is when it will all start to tie together. If you're not overwhelmed at the end of this 25-minute problem, then you're not really paying attention because there's a lot going on. It will get easier. I'm sort of giving you an example that has it all. And then most of the problems get a little bit less involved, I guess. So if you could, turn in that giant packet of papers, which we're nearing the end of, in your notebooks, it says PV diagrams, quantitative analysis, and it looks something like this. You got it? Because here's where we're going. Well, these were the notes from last class. And just again, a review of gas laws, the ideal gas law, the first law of thermodynamics, and PV diagrams that have these isotherms. Now, the thing that always frustrates students is they feel like they've got to get those isotherms drawn perfectly. You don't. Just kind of make them go whoop, whoop, whoop. The lowest one has the lowest temperature. The highest one has the higher temperature. And just kind of go with it from there. Don't overthink it. The four processes you've got to know the vocabulary for: isobaric, isometric, isothermal, and adiabatic. Okay, so we're going to jump right into this example. If you don't feel great by the end, it's okay. I'll get you there, I promise. I know you guys can do this. So, I took the liberty of drawing in some pictures before in an effort to speed things up. Let's first just focus on what the question says. It says, exactly 1 mole of an ideal gas at 300 Kelvin and 1 times 10 to the 5th pascals is at pressure A, undergoes an isometric process to reach a pressure of 2 times 10 to the 5th, B. At this point, it is allowed to expand adiabatically to its original pressure of 1 times 10 to the 5th and a temperature of 455 Kelvin. This is now it is compressed isobarically to its original point A. If you're not lost already, man, you're not. You guys are good. That's a lot of information. So you know what I do? First things first, I organize my information. The process went from A to B to C, back to A. So let's look at what information I know at each point. So if I think about what is available in this question, pressure 1 was at 1 times 10 to the 5th pascals. If you didn't draw this in yet, do it or push pause. V1. Did it give me the... No, it did not. But it did give me the temperature at 1, which was 300 Kelvin. P2 is 2 times 10 to the 5th pascals. Did it give me any other information? Isometric. That means the volume at 2 is equal to the volume at 1, but I still don't know that yet. Okay. At C, it says it's allowed to expand adiabatically to its original pressure. So P, I should have called these C and A. Darn it. I'm going to make that C is back to 1 times 10 to the 5th. Now, in a problem like this, have you guys ever seen me solve a 25-minute problem and not make multiple mistakes along the way? Yeah, I know. That's where this is going. Okay, C. The volume at C we don't know, but the temperature at C we do know is 455 Kelvin. And then it goes back to A at the beginning. So 1 times 10 to the 5th. I'm sure you guys are putting units on everything, of course. The volume we don't know. The temperature we do know is 300 Kelvin, and it's 1 mole. Okay. So if I were to maybe add one other thing in here, I might use the words from A to B. It's isometric. From B to C, It says it was adiabatic. Adiabatic, a fancy word for really fast, so no heat flows. And then from C to A was isobaric. Okay. Still feeling not confident? That's okay. Let's look at what we can fill in. Now, this is our first example. I organized two charts for you. One will allow us to collect sort of the P, V, T, and U. U is internal energy of the gas. Now, I need all of that information so that I can fill in the big chart down here. This is the one we care about. The change in internal energy, the heat, and the work. And the answers we really care about at the end is for ABCA. No, ABCA. What is it for the entire system? That's what we're really trying to find in the end. Okay, so where to begin? Well, I know that the ideal gas law tells me that I can find the volume right here pretty easily using perv-nert. So if I say, I'm going to say to find VA, PV equals nRT. Maybe for today's video, I will occasionally just shut up. Stop cheering, Josh. Just kidding. I'd be cheering. See? Can't shut up. Now, this is unfortunate because normally this is when I take a break and then I pretend I'm doing it. And then Adam gives me the answer. And then Amanda backs it up. And I got 0.02493. But you know what? Let's make that 0.025. We're going to round a little bit today. Let's be nice to ourselves. I believe in current language we'd say, be good to yourself. So we'll say 0.025. All right. Now, what else do we know? What else can we find? So process A to B. B to C is adiabatic. I guess for C, we can determine, for B is isometric. Oh, so it's the same volume. Check. And then C. C, I believe I could find the volume again by doing the same process. Anybody else get 0.038 meters cubed? Good. Me too. Let's fill that in. Now, do I need the temperature? Possibly. So just for kicks, I'm going to find it because I like to be prepared for anything. And if it turns out that we don't use the temperature for B, so be it. It's not a big loss in terms of time. What else are you doing? So let's do it. To find T at B. You know what? Just to shake things up, I'm going to compare two positions because what I have here is a closed system. I could say PA VA over TA equals Oh, and the volumes are the same. So the temperature at B, just got to cross multiply here a little bit. Oh my gosh. The pressure doubled, right? So if the original temperature is 300, oh, how many of you saw that ahead of time? How many? Good for you guys. That's why you're ready for this. Actually, that's why you're ready for this to be over. Because you're ready. Now I'm going to fill that in. So that temperature then is 600 Kelvin. Okay. Last thing to fill in my information. To find the internal energy, U. I could do it a few different ways. I could do 3 halves PV. Yeah, let's do 3 halves PV. That's the easiest. So I'm going to show my work for the first one, and then I'm just going to fill in the answers for the other. You guys cool with that? Now, is there some rounding involved? Yes. Let's knock it all banana shape. I got 3,750 joules. Now, because the temperature doubles for B, I'm not trying to show off. I'm just trying to say, because the temperature doubles for B, if I were to use the formula, internal energy is 3 halves little n RT, and 3 halves n R is the same. Internal energy is directly proportional to the temperature. So if you double the temperature, then the internal energy will be doubled as well. If you didn't catch that, plug in the numbers. That's what you get, I hope. Lastly, for the 455, you know what? I'm going to find that for C and plug it in. So U of C is 3 halves that number. You know what? I just plugged it in the other way, and I ended up with 5,700, which somehow just feels like a better number to me. The other one I got 5,671, and because of the rounding with the constants, there you go. Here's the crazy part. We haven't done anything yet that you didn't already know from gas laws, except for a couple of vocab words. Let's go up to the graph. When it comes to this graph, I took the liberty, before I started, to draw in a few different isotherms and to plot some points. I knew if there was a point I was going to get messed up in this example, it would be this. So I drew in 3 curves. And the bottom one's going to have a temperature of 300 Kelvin, and the top one is 600. We already found this one to be 455. So I drew it kind of in the middle. Here's the thing. For A, if we start A at this point, it would have a volume of 0.025. You see it? So we'll let this pressure be equal to 1 times 10 to the 5th. So I double the pressure as it went up to B. It's isometric, so it's a vertical line because the volume doesn't change. From B to C, it's adiabatic expansion, which I will explain more next time. But how I think I would take it for right now is it expanded, so it got bigger, and the temperature dropped. Now that's a curve. Do you see that curve? No, you don't see that curve? Well, it's there. Look again. That's a curve. Now it's at position C. And then it goes isobarically back to A. There it is, your very first PV diagram. Aw, take a snapshot. There it is. Okay. So, how do we utilize the first law of thermodynamics to solve up this problem? Well, when we're looking at processes from A to B, let's just fill in what we can, right? So U, the internal energy of the gas at each point, has been calculated, and the change in U, I'm pretty sure that's just subtraction. So as it went from A to B, you would do to find the change in U for AB is simply the internal energy at B minus internal energy at A, final minus initial. So numbers work out kind of funny here, the very clean way. You're welcome. The change in internal energy increasing. I'm going to put a plus. I am. You don't have to. I understand the lack of sign means positive. Let's look at it as it goes from B to C. B to C. So 5,700 minus the 7,500. And I'm going to get negative 1,800 joules. Just the change in energy. As it went from B to C, look at the graph. The temperature decreased and internal energy is directly proportional to temperature. So as it got cooler, it makes sense the internal energy will be less. Good. Now, C to A. C to A. It goes from 5,700, right? Back to 3,750. And you should have got negative 1,950 joules. Could have found it another way. I could have said, well, I know the total change in internal energy, as that Super Cram video said, if you go back to the same place you started from, the change in internal energy is going to be 0. Why? Because you're at the same place you started at. Of course, it's going to be 0. It's only for a complete cycle. Now, how do we find Q and work? Wow. Okay, a lot going on. I know that the change in internal energy is equal to Q plus W. This is the first law of Thermo. And this is what I go back to when I need to solve things up. Not me. It's what everybody goes back to. So how do we do it? Well, we know delta U in each case. But do I know the other pieces? I'm going to start with one. From B to C, the process is said to be adiabatic. Adiabatic means that the heat flow happens so quickly, or the process happens so quickly that there is no chance or no time for heat to flow. So Q in an adiabatic process is going to be 0. Now, to find the work for process, let's say BC, I'm going to show it anyways. I'm going to show it. If we take BC, which is negative 1,800, equals 0 plus the work, what's the work going to be during process AB? That's right, negative 1,800 joules. Okay, picking off the low-hanging fruit here. Good. What else do I know? Well, I realized as I was talking that I probably should have given you a lesson first. This is the problem of having 20-minute lectures. Work. What does work equal to? Well, work is force times displacement. Work can also be the change in energy, but not change in internal energy. So I don't want to go down that route. Instead, what I want to say is that work can be equal to the change in the pressure and volume. Now, as the volume increases, then the work done on the gas is negative. So I have to introduce a negative sign to the front. Negative P delta V. Now, we're doing this as a non-calc based class. So we're only going to look at this when we're going to calculate this when the pressure stays constant. Okay? So what does this tell us? Nice. You see it? Nick, do you see it? Yeah, that's right. If work is negative P delta V, right there. What if the change in volume is 0? What if the change in volume is 0? What's the work? Nice, Connor. Thank you for bailing him out. Then the work is 0. Let's look back up at the graph. Look at A to B. Did the volume change? No. That means the gas was neither compressed or expanded, so the work done on or by the gas, 0. Check, check. Now that I know that, I can find easily enough, you see it, that the heat added to the system must have been net plus 3,750 joules. Good. How about C to A? C to A gives us an interesting situation. If I want to find the work done, which is the product of P times the change in volume, what could I do to the curve from C to A? Oh yeah, what would Micho say? And actually, I don't know what he would say, but what I would say is that we can find this, which is known as the area under the curve, right? The area under the curve would be the work done on the gas during that process. So, can I find that? It would just be the product of P times V. So, you know what? I'll write it out. I'll write it out right here. So to find the work for C to A, find the area under the curve. For those of you who are just tuning back in, yeah, we're still in the same problem. So the area under the curve, work equals negative P, change in volume. I flip those, let me flip them back. Final volume minus the initial volume negative 1,300 joules. Oh, negative? Is that negative? No, what happens to the two negative signs? That's right, they cross out. And I get positive 1,300 joules. So then, to find Q, stay with me, we got this. To find QB, to find the heat during process CA. let's say the change in internal energy equals Q plus W. The change in internal energy is negative 1,950. The change in work is plus 1,300 joules. And yeah, I don't solve for the variable with these. I plug it in. Hope you're okay with that. I got the heat flow is negative 3,250 joules. Okay. Now, wake up, wake up, wake up, wake up. Here it is. This is your moment of Zen. The change in internal energy of the gas is zero because it repeats and goes back to the same exact point. The heat in the system, there was 500 joules of heat added to the system in total. Okay, 3,750 joules of heat was added during process A-B, and then during process C-A at the end, 3,250 joules was exhausted. Yes, exhausted. 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 What else has exhaust? Oh yeah, the tailpipe of your car. Everybody always thinks it's just the smoke, but that tailpipe is hot. It's also getting rid of excess heat. That 3,250 joules of heat that flows out of the system is exhausted as useless heat. Now the work done on the system, if I add up all the works, I get negative 1,800 plus 1,300, I'm going to get minus 500 joules of work. Now, that's work done from the perspective of the gas. But the negative 500 joules of work means that the gas expanded out and did a net total of 500 joules of work pushing out. Yeah. Now, looking at this, there it is. There it is. We just took heat energy, which could have been obtained from a variety of different ways. I think the easiest to think of is a gasoline engine, right? Heat went into the system, and we took heat in a gas and turned it into useful work. We turned heat into work. That's the power of the first law of thermodynamics.